So conventionally, we know that when we have identical particles and we swap them, let's say fermions, they get a negative sign. Bosons do not change. Then we also have anions, which are found in 2 dimensions, and they have they interpolate between the two.
Mhm.
So what happens when we swap these paraparticles?
Right. So you should think about these paraparticles actually having other information attached to them. Figuratively, can refer to it as a color. So you can think about having a red particle or a blue particle, for example. And so what really happens is that color changes as they swap
Mm-hmm.
around each other. Of course, not a real color. This is just, again, language. Sometimes we also call it flavor,
Mm-hmm.
which makes it even more clear that, it's something made up. But if I take ordinary fermions, you can also tag ordinary particles with some sort of label. Sometimes spin in physics, little magnetic moments do this. And the point is that degree of freedom, that tag just follows the particles. So if I swap a red particle and a blue particle and I move them around each other, the red and blue just follow the particles. In contrast, for the paraparticle, other things can happen. Red can turn to blue. Maybe they both change to purple to some new label. And there are very specific, discrete types of allowed rules that come up for these paraparticles.
I see. So we can actually get a little deep into this. So these internal degrees of freedom that you just mentioned, why are they? So what are they, and why are they inaccessible to any local measurement?
That's a very good question. So in terms of the what are they, it's a little hard to say much because we don't have real physical examples yet where somebody's discovered a paraparticle in nature. And so all we have is some math, and in the math, they really are just labels on these particles. Very much like if I said I had 2 types of fermions, I could attach a label saying, am I type A or type B? Maybe am I a electron or am I a muon, right? This would be just like some label I could attach to the particle telling me which is which. And so I can't tell you a lot about the what they are, but in terms of why they can't be detectable locally, this is a really key property of the paraparticles. So this color is something that we literally say nothing can go and measure. It's sort of physically hidden, at least as long as you're only allowed to measure stuff around that particle. And the reason is indistinguishability. The whole premise of all this, the sort of particle statistics, is that you have identical particles. So you can't tell if you swap them.
Right.
But if you could actually see that internal index, you would see that it changed somehow under the swapping. And so it would ruin the indistinguishability of the particles. And so then you could worry if you can't see it, does it have any physical effects? Maybe it just doesn't matter. But that's not the case. It has many, many physical effects.
I see. So it is actually forbidden for any local measurements to ever see them.
That's exactly right.
I see.
There are some very technical caveats to this. It turns out if you live in a finite universe and you go to the corner of that universe, you can measure the internal index at 2 corners, maybe 4 corners, something like this. Also, if you had like defects in your space-time, maybe there are defects, in your space-time that can access this. But maybe let me be a little less, fundamental about this. We actually think about these particles, maybe they can occur in like a chunk of material. And there it could be that there's just some defect in the material, and at that defect point, that's where paraparticles can get created.
I see. And by chunk you mean the bulk of the material.
Exactly. The bulk, away from the surface, away from any other edges.
I see.